Okay, so thank you very much for the invitation, and it's a great pleasure to be here with the spring weather. Without telling you. Okay, so I'd like to talk about the character variety. So let's just let X be a compact Riemann surface. Or something else similar. Yeah, so, well, the example is going to actually be P1 minus 4 points, for example, okay? But we'll get to that. But for example, if it's an orbifold, if it's a Riemann surface with orbifold structure, then everything is very similar. We might want to allow some more general monodromy. So then let's look at the character variety, which I'll call M Betti for Betti moduli space. So it's just the, and maybe let's choose a base point. It's just the maps from pi 1 of our Riemann surface into SL RC. Okay. So let's fix for now a group just matrices of determinant 1 divided by the conjugation action. And the quotient is a GIT quotient. Okay. So let me explain this very briefly, but let's just say this is what's usually known as the character variety. R is some integer, say 2, 1. Okay, and this is actually an affine variety. Why is that? It's because if we just take the this before dividing by the conjugation action, then it's a closed subvariety of the product of 2G copies of the group. Remember that pi 1 has pi 1 has generators alpha 1, alpha g, and beta 1, beta g, and subject to the relation, subject to this relation. So the representations are just 2G tuples of matrices which satisfy the same relation. So that's a closed condition. So we can write it as spec of a ring. And the action, so the action is by mutual conjugation of these matrices by the same matrix. And the quotient, the GIT quotient, so the point is that the GIT quotient of an affine scheme is just the spec of the ring of invariance. Okay, so this guy is just the spec of the ring A invariance by SLR. Okay. But now we actually know a little bit more. We have what's maybe known as Procesi coordinates. Which is that this ring A this ring is generated by functions of the form trace, a function which sends a representation to the trace of rho of some group element. So for every group element, we get a function trace of the representation, and so that's why this is this ring is viewed as I mean, these are viewed as characters in some way of the group. Okay? So that's why it's called the character variety. So now, since it's affine, unless it happened to have dimension 0, but in general, as in this case, for example, it will not. Since it's affine, it has to be non-compact. As soon as the dimension is positive. And so we would like to understand, we would like to look at the what happens at infinity. So just in this form here, not too much is really known well, maybe I'm saying a little bit too much there, but not too much is really known about this. So what I would like to first do is relate this to some other spaces. Okay. So there are. So this comes from the fact that so X has a structure of algebraic variety over C, and here we've just used the topological structure. We've just used the fundamental group. So we can use this structure to provide some other spaces. There are some other spaces which are isomorphic to the character variety. So let me just write the main ones down here. So E is going to be a vector bundle, which in our case for the group SLR should be a rank R vector bundle with an isomorphism between the determinant and the trivial bundle. And we just have a connection operator. In the case of a one-dimensional, we're on a curve here, so it's one-dimensional, there's no omega 2x, so there's no curvature condition here. And this is up to S equivalence. So S equivalence means that if two vector bundles with connection have if two guys are irreducible, then S equivalence just means being isomorphic. If they happen to be reducible, S equivalence means that the Jordan-Holder series has the same quotients. Okay? And that's the guy which corresponds exactly to the relation that you get when you do this GIT quotient here. Algebraic, yeah, this is an algebraic moduli space for X. And the connection operator is also algebraic. Yeah. Maybe trace, sort of a trace equals 0. Which, I mean, it really means that it means the top exterior power, the connection induced on the top exterior power should be the trivial connection. Then Hitchin introduces a new moduli space, which we could call MH for Hitchin or Higgs or something, but let's just call this M Dolbeault because that fits into a sort of a more motivic kind of picture. So E is going to be, again, a vector bundle. So this is the moduli space of Higgs bundles, which are a vector bundle, and a phi is exactly the same, formally the same type of map as a connection. But this is just an OX linear map. And it's in this place that we can just say trace equals 0. Now, the Riemann-Hilbert correspondence tells us that we have an isomorphism of complex analytic spaces. And the Hitchin equations tell us that we have a homeomorphism Furthermore, well, we're not going to talk about this more today, but the complex structure, this is sort of tourism, one of the interesting things about this is that this homeomorphism is not complex analytic. So we get a new complex structure, and that new complex structure together with the old one give two of the three elements of a quaternionic structure, which it turns out to be hyperkähler. So, sorry. So let me let's see. So what I would actually like to talk about maybe a little bit more is the behavior at infinity of this isomorphism. But we should think of that as being pretty similar to the behavior at infinity of this isomorphism. Maybe I'll just say why. So here is this is Deline's in fact idea is to introduce a moduli space a new moduli space sort of interpolating between these two guys. Well, yeah. So infinity means that our matrices rho of gamma I are going to get big, basically. And in this case, it means that our connection is going to get big. And that's what I want to exactly discuss now. So in fact, so what we'll do with this today is we're going to use this to compactify these spaces. So now I'll use the index Hodge because this is actually the Hodge filtration. This space is sort of the Hodge filtration on this guy. And the associated graded of the Hodge filtration is this guy. So that's an interpretation. Sorry, I should have added here. We need to add a condition of being semi-stable. I guess the degree is 0 is already good. We're dividing by S equivalence in the same way. So the idea here is to observe that these two conditions are extremely similar. This being a connection means that it has to satisfy a Leibniz relation. And we can think of this condition, being OX linear, as just having the same Leibniz relation, but just with a 0 in front of the derivative. Okay, so this is what Dewey called lambda connection. Okay, so again, E is a vector bundle of rank R, determinate, trivial, maybe to start with, lambda. Here. Lambda is just a parameter, okay? A complex parameter, and nabla is an operator from E to E tensor omega 1x, such that nabla of A times E is equal to A nabla of E plus little lambda of dA times E. So we should add a condition of being semi-stable to get a nice moduli problem. This condition of semi-stable is automatic if lambda is different from 0, but it needs to be added as a condition for lambda equals 0. And we then divide again by S equivalence. Okay. So let's see. I guess I can put this here. So we have I have this moduli space, this Hodge moduli space over the affine line. At the point 0, we have, this is just, if we specialize to lambda equals 0, this just becomes a OX linear operator. So that's the same as here. If we specialize to lambda equals 1, this becomes a connection. Okay. Furthermore, if we specialize to any lambda different from 0, they're all going to be the same moduli space. So we can just rescale. So GM okay. So we have a rescaling action which covers the standard action here. So all the fibers different from 0 are the same. We just get a deformation from this space to the Dolbeault moduli space. And we can use this to compactify. We could, well, maybe just will not say that here, but of course the same thing will work for compactifying M Dolbeault itself. Maybe I should just here we have the Hitchin map. This action preserves the fiber over 0, so we have an action on here that covers a weighted action here, not the standard action, but an action with some weights, and this is a proper map. So to compactify the fiber over 1, what can we do? Let's define a sort of a star here, which is the complement of the origin here. This is what's sometimes known as the nilpotent cone. It's the set of Higgs bundles where this phi is nilpotent. And then if we just take, so we just throw that out. That's like, so it's basically what we're doing here is basically like defining projective space by taking affine space minus the origin and dividing by a C star action. Okay. The origin corresponds to this F inverse of 0. That's roughly speaking sort of all the stuff which are going to be limits of orbits. Maybe roughly. I mean, it's kind of the limit of everybody as t goes to 0. Okay, so we take the complement of that, and then we define the compactification to be just this guy modulo the GM action. The image of this M de Rham fiber is an open set, and the complementary divisor is just the what you get by taking the Hitchin moduli space, again throwing out the inverse image of the origin and dividing by C star. Now, what I'd like to say here, so this will be a little bit, maybe I can erase my hypothesis because we'll have to erase this hypothesis to say that, but in this more general situation, something similar here. You can often have a situation where these moduli spaces are smooth. Okay, so often in the orbifold or other cases, these guys are smooth. If in the precise situation I said here, they're not going to be smooth, and you can tell when it's going to be smooth or not. The non-smooth points are the places where you have reducible representations. So you can cook up things so that you don't have reducible representation. Maybe one of the easiest ways of doing that is to take representations into PSLR. Then there's a degree, and if the degree is prime to R, then there will be no reducible representations. But you can also do some other orbifold things. And in that case, the compactification it's not really going to be smooth exactly, but it's going to be smooth if we take this quotient in the orbifold sense. So if you think about it a little bit, it turns out that there can be finite subgroups here, roots of unity, which stabilize some points. Those points will give sort of conic points if you just try to take the GIT quotient here. But if you take well, it's not really GIT, but a quotient, an actual quotient. If you take the orbifold, we still get a smooth guy. So the compactifying divisor in this picture is just some smooth divisor. So it looks like it might be nicer. So now the question that we would like to understand is, how can we understand what's happening? So question. So the question is to try to understand the Riemann-Hilbert correspondence. So where did I write that? Let's call this RHC. So we would like to try to understand this map between this space where we now have a smooth compactification and this space where we don't know too much about the compactification. Now the way we're going to do this is by at least this is a difficult question. But so what can we do here? We can try to probe this question. Let's just look at a curve inside here, which is transverse to D. Okay. Now, what is a curve inside here going to look like? So a curve inside here is going to be, so if we want to make a curve inside here, we could just make a curve inside here. Okay. Algebraic curve, yeah. can make a curve inside here, but it should go towards infinity, so it should go, where are we here? It should sort of map, for example, down to A1, isomorphically down to A1. The curve should approach the divisor, which is the non-nilpotent part of the moduli space of Higgs bundle. So our curve should come from a family of lambda connections, and I don't know quite why, but I usually prefer to have something getting big rather than something getting small. And let me just index this by t. Okay. So nabla t oh no, sorry. Let's call this lambda. But well, let's call nabla t is t times nabla lambda. So this is a connection. Okay, so what did I do here? I just sort of inverted the coordinate here to get something that's getting big. Then I use this rescaling property to rescale my lambda connections, which are where lambda is getting small, into just a family of connections. Okay. Which should be getting big. And to just make things simple, let's just assume that our bundle E is a fixed bundle. And we have this family nabla T. And we would like the limit to have to be a Higgs field. So E say a stable, for example. So we would like the limit to be a Higgs field, so that the limiting guy, so this guy is going to be the limit. This guy is going to be the limiting point inside here, inside the divisor, which is somewhere in the fiber over 0. And the easiest, again, the easiest case is, let's just define nabla T to be given by some fixed connection plus T times this phi. But so the picture should be about the same. I mean, I guess this is not really written down anywhere as far as I know, but the picture should be about the same if we do some more general family of connections, and if E is allowed to be, say, a bundle which moves. And I guess that's what's actually going on in some papers of Guyotto, Moore, and Knightsky. Okay, but just to be completely explicit, let's just choose a family looking like this. Okay. Now now we can take the Riemann-Hilbert correspondence. The Riemann-Hilbert correspondence takes this family of connections to a family of representations, rho t, from pi 1 of x into SLRC. So rho t of a group element gamma is the transport. So let me use this notation. The transport from the point x0 to the point gamma x0. So this is the transport of the connection nabla t from, now let's put a little tilde here also. So now let's move up to the universal cover of X. So on the universal cover of X, we're sort of, it becomes contractible, so there's no question about a choice of path. And we can just talk about the transport from one point to another. So let's just use this notation for this transport. So this so in general, so more generally, this is perhaps a slight abuse of notation. These were points in the universal cover, but these are the values of the vector bundle on the points downstairs. Okay. So we get to the following setup, and this is just a classical problem of solving ODEs. And it's usually called some kind of WKB problem. WKB is Wenzel, Kramer, and Brouillerin from around the 1920s. An asymptotic problem. So the problem here is we're trying to understand what happens when t goes to infinity. So I'd like to do two things here. I'd like to first state kind of a general principle, sort of relation, sort of a limiting harmonic map. And this is about joint work, recent joint work. With Kazarkov, Alex Knoll, and Panav Pandit. So what can we do here? And but I should say maybe also based on work of Perot, Guyota, Mornitsky, and maybe motivated by Kontsevich, Soibelman, Bridgeland, Smith, and so on. I should probably also put Haydn. Haydn, Kazarkov, Kontsevich, recent paper, and so on. So what's the idea? The idea is actually to just, Perot generalizes the classical Morgan-Chalin compactification of the character variety. So the Morgan-Chalin compactification, I guess, was for SL2, and Perot's paper treats the case of a general group, basically. And the points at infinity are actions of pi1 on R buildings. This is in a sort of a heuristic or intuitive sense. This has been sort of, you might say, clear for quite some time, which is that somehow or other points at infinity in this character variety should be considered as some kind of representations of pi1 with values in some kind of valued field. Okay. So the heuristic is that points at infinity Sorry?
You're looking in general, just in matrices, you said you had general group.
Well, I don't know. I think I gather that this general theory. I don't remember. I gather that this theory, if it wasn't explicitly stated in the paper, in any case, is certainly intended to work for any reductive group or something. I guess we're just taking SL. I'm not talking here about other groups. In any case. Okay, so
I guess I'm asking the difference between 2 by 2, which is moving channel.
yeah. Here we're taking an R, which is, well, R is some. Well, the point is that we go from a tree to a building, basically. So the idea is to think of points at infinity in the character variety as representations from pi1 into SLRK, where K is some kind of valued field. So, for example, K could be, say, C round brackets Q or something like that. Typically, a curve, just a little germ of curve in the algebraic variety is going to be something like that. Okay? And then we get an action. Then this guy is going to act on the Bruhat-Titz building. Okay. So let me go over here. So that doesn't work out completely well, I guess. Well, I mean, it probably does in some way, but in fact, I guess there probably should be a Berkovich space compactification. That's probably the real thing that you actually want to understand. But so what's happening in Perot's work, in Morgan-Chalin and Perot's work, is that we choose an ultrafilter. So So we choose an ultrafilter on, say, the set of sequences, or maybe just the set of real numbers, and we rescale the metric on this symmetric space. This is a negatively curved symmetric space. We rescale it and then take some kind of Gromov limit of this guy. And that's the way you can put then you get an R building, and you can get actions of I mean, if you take a sort of a sequence of points going out to infinity, then you can get an action on a building like that. So in our case, here you mean. Yeah. The t should go to infinity. Okay. In our case, the ti's, the rescaling factors, are the same as the value t up here. So perhaps we should maybe choose a subsequence of t's, or speak about ultrafilters on the real line, or something like that. Okay. Well, anyway, so what we can do is we can fix any metric on the bundle E, but independently of T. And then this allows us to speak of, then we can define, let's just write this down. The exponent is the limit, so this again depends on the ultrafilter, of 1 over T times the log of the absolute value of the transport matrix. Okay. So fixing the metric H here allows us to define this, the size of the matrix. Okay. So this guy is basically the distance. This is, roughly speaking, the distance from maybe this is not precisely the distance, but sort of asymptotically, this guy is going to be basically the distance between the points, the images of the points P and the point Q by a map. So let me just not write down this map. I don't have really the place or maybe the time. But just the map that you get by using the transport matrix to bring all the metrics back to the base point. Okay. So we just bring all the metrics back to the base point using the T transport matrix. Now this is going to be the distance between the two metrics, basically. And so here we've just rescaled, and so this guy is just going to be the distance between the image points of a map to this building. So Perot's theory, sort of a group, let's just say a groupoid version. Perot's paper was only written for getting a limiting action of the fundamental group, which, roughly speaking, is going to correspond to understanding the images of these points of the form gamma times x0. But we can just look at the image of any points P and Q. That's kind of essential for what I'll be saying next, actually. But it's just an immediate generalization.
This final action on the building is what kind of thing?
Sorry?
This final action that you're getting on this.
That's the big question, I mean, you might say. Just some action on the building. Yeah. It's an action in the category of our buildings or something. Okay, so we just get a map from, we get a pi 1 equivariant map. Pi 1 equivariant for Perot's action, for Perot's action. We get a pi 1 equivariant map from the universal cover of X to the building where the distance between the image points is just this exponent. So now what does this exponent say? This exponent basically says that, so very roughly, the size of the transport matrix looks approximately like e to the u t. But let me just underline very roughly here. Well, for one thing, so if the, sorry? Yeah, thank you. So we discussed this on Friday. The Finsler distance is the, well, there are some natural coordinate functions on the panes of the tree of the building, and the Finsler distance is sort of linear. It's the maximal linear distance. So very roughly, this exponent, it just means that the size of the transport matrix is exponential of something times t. And this nu pq is just the exponent, which is the constant that goes here. Okay? So we can, yeah, I mean, if you think about solving ODEs, right, here we're just, to define this transport matrix, we're just solving this system of ordinary differential equations, which is the connection nabla t. Okay? And we know that the solution of a system of ordinary differential equations is going to be exponential in the size of the coefficients. Okay? So we know, for example, that that this limit exists. I mean, we know that these guys are bounded, for example, in t as t goes to infinity. So there's going to be some estimate of the form this size is less than or equal to e times some constant times t, and we would just like to find the best constant. Okay? So that's, as I'm erasing this, I mean, so that's like a very extremely first question about what you would like to know for the Riemann-Hilbert correspondence. Just how big is the matrix? We go from M to Rham to M Betti. Here we have a pretty good idea of how big things are, although not so easy to actually define precisely, but roughly speaking, 1 over the distance to the divisor at infinity. Okay. And here we also have a pretty good idea of how big things are, which are just given by the size of the matrices. And the first question is just, going from here to here, how big is the image going to be? Okay.
So do Stokes lines play a role in this too, or not?
Yeah, so I have an example to do here, but this example is going to sort of go into the next. I'm talking again next Tuesday, I think. So maybe I'll start with the example if I can today, but then that will continue on Tuesday. What I just wanted to say here is sort of relating back to what happened on Friday, which is that so here we have our conjecture. From our recent paper, or two, in fact, this is really from our more recent preprint just a few weeks ago, is that there should, so for generic fees, there should be a universal map to a pre-building which depends only on well, let me just briefly say this, depends only on the eigenvalues of this Higgs field phi. So what do the eigenvalues mean? It really means the spectral curve. Which is the image Sorry? Phi. Because, sorry, I just erased this, but we're discussing this family of connections E, comma, nabla T. And nabla T is nabla 0 plus T times phi. Okay? Sorry, but thank you for asking that, because I realize I've forgotten to say something important here, which is the theorem. The conjecture comes after the theorem. I'm sorry. Maybe I should. Thank you for that question, because I realize. Yeah. The question: what does phi have to do with everything here? So the theorem here is that the classical. The theorem. That's the proof. Is that the H omega, as it's called. Yeah, this map here is a locally harmonic map with differential d of H omega is the real part of phi, where phi is phi 1, sorry. Where phi is the phi i's are the eigenvalues of the eigen one forms of the Higgs field phi. This is in our situation of a connection there. So the idea is that now this tells us something about the harmonic map. You were asking, what properties does the harmonic map have? This is the main statement about the properties of the map, and the proof uses. Yeah. This is with respect to the Euclidean metric, not the Finsler one. Although, if that makes sense, it would probably be true also, I guess. But I'm not sure. And we don't need to specify the metric on the Riemann surface because since it's real, since it's a Riemann surface, that's independent of the metric. So the proof uses the classical local WKB approximation. Okay. Which is to say, if our points P and Q are close together and joined by a non-critical path, so a non-critical path is a path where these differential forms, real part of the phi i's, all stay in the same order along the path. Then classical WKB theory from 1920, perhaps, or something like that, tells us that we can actually estimate this exponent precisely. We can get precisely the exponent. So we get the distance, and we can more generally do the same thing for, say, exterior powers or something to tell us really where we're going inside the building. Okay, then the question now becomes, in order to get a good control of this exponent, then the question becomes, how can we understand harmonic maps if we're given the differential? Okay. So now we have a harmonic map, and we know it's differential. We'd like to just understand the harmonic map. And that's where this conjecture comes in. So I guess I'm sorry, I'll be covering this board. I guess I'll put this up here. So the conjecture is that for a generic, just say spectral curve phi, there should be a universal map to a pre-building. Call this H phi. So that for any map from H from X to B, to a building such as, for example, this cone omega, with dH equals real part of phi, there exists a unique factorization of the form x tilde into like that, okay? And furthermore, this f preserves distances. Preserves Finsler distances. So on Friday, I tried to, at least at the end, explain very briefly how we are seeing the construction of this map in the case of SL3, but it's only conjectural. Let me just mention in the case SL2, so this is the sort of the classical case which has been very much studied by low-dimensional topology. The classical case SL2 is that phi is just a quadratic differential. And this B, this pre-building exists. It's the space of leaves, which is an R tree of the quadratic differential. Okay, so that's the relationship with what's known in low-dimensional topology. So we're, roughly speaking, trying to extend this notion of the space of leaves of a quadratic differential into higher dimensional buildings. So far, we only can really understand the case of SL3, and even there it's fairly highly conjectural, although we claim to have a procedure which should construct this guy. Now, one perhaps interesting point is that this genericity condition Yeah.
But F is only preserving Finsler distance.
But no, F is a folding map of buildings.
Okay, so it's folding, so it's essentially outside of the folding, it's looking at isometric even folding.
Yeah. And I guess I have to think about it. I think maybe in this conjecture, in the situation where we are in here with phi generic and everything, maybe the part of the statement is that F is actually not folding. I mean, F a priori would be folding, but part of the conjecture that it's distance preserving is that it doesn't fold, in fact. So F is actually an isometric embedding. Now, let me just say that the genericity condition is that in the spectral network defined by Guyotto-Mornitsky associated to the spectral curve has no what they call BPS states, or at least they used to call BPS states. Which I heard a talk by Andy Knightsky where he was more reverting to, I guess, what's the standard notation in this theory, which is saddle connections. Let me see. I should stop here, so I guess I won't. I'll be getting to my example in the next talk. Sorry about that. Let me just draw an example of what this means to have a saddle connection. So in the SL2 case, a saddle connection just means that we have a branch point. At branch points, the foliation has 3 leaves that come out of it. A saddle connection means that the 3 leaves coming out of some branch point are the same. One of the 3 leaves coming out of a branch point is the same as one of the 3 leaves coming out of a different branch point. Okay, this is SL2. In the case of SL3, for example, or higher SLRs, there's not a single foliation. The foliations are really given by the real part of phi ij, the differences between pairwise differences of the forms. Okay, and then there's this interesting new phenomenon which can happen, which is called collisions. So now the foliations are labeled by, say, ij. The new thing that can happen, this was kind of the thing, this was the observation which really motivated our whole project, was to understand this, this thing in the new papers of Gaiuto-Moronitsky. So the ij foliation lines coming out of an ij branch point can collide with the jk foliation line coming out of a jk branch point and create a new guy, I mean, this would be a foliation line which would go somewhere, but it's not going to generally hit any kind of a branch point. But this guy is obtained by a collision, and now it's labeled IK, basically. Okay? Then, in fact, if you look in the papers of Gaiuto-Moronitsky, there's many papers, and they have many beautiful pictures, in which case you get these gigantic networks of things like that. Well, let me just sort of draw maybe a slightly more complicated one here. So this might have been a branch point, and then we have IK. Ij back to J, or let's call this even L or something. Then we here would have K, L. Then maybe this one might have gone to itself a branch point. Okay. So here would be a BPS state with two collisions. Okay. So what they say is that the generalization of what were just saddle connections in the case of a single foliation coming from a quadratic differential, now it's some more complicated geometry where we have a bunch of different branch points labeled by pairs of indices, and these guys can collide, and a saddle connection is sort of a compact segment generated by everybody. Okay. So now what it seems to be the case, so this is again is very conjectural, but it seems to be that these saddle connection things are exactly the guys which determine the non-generic values of phi. Okay? And that's going to be some kind of wall crossing situation in the space of forms, phi, basically. So maybe I'll stop here.